Hello everyone, I'm Somesh. I will be presenting some of the photovoltaic grid forming strategy investigation using hardware experiments. Um, the agenda of this presentation, as we follow, we will discuss a little bit about virtual inertia, why virtual inertia is important, how can it support the grid that is becoming increasingly, with increasing renewable penetration, how virtual inertia can support the grid, and how PVs can support the grid as a virtual synchronous generator. We will also discuss the distribution network that is under consideration and the results that we obtain using Typhoon hardware in the loop 604. So now to come to why virtual inertia is relevant and why is it important. The grid frequency in an AC system, it essentially determines that what is the balance, real-time balance between the generation and the loads. When we have an event such as a fault or a loss of load or a loss of generation or just a load change, this swing equation comes into play, and that the difference that determines either the generator is going to accelerate or is it going to decelerate. But what matters is how soon it is going to come back to its original position, and that's where the system inertia comes into play. So yes, system inertia is akin to the resistive element. It's the mass that restricts the sudden change of frequency and thereby obviating the use of the rate of change of frequency relays, the Rockoff relays. Power electronic components such as photovoltaics, wind, they are inverter-based sources, so they cannot generate their own frequency. So they are frequency followers, so they are negative loads. Negative load means they are not helping in providing the system inertia at all. But do photovoltaics help? They do help generally, when especially in a large scale farm. Nowadays we have regulations from the electricity authority that in case of a frequency swell, especially in case of a frequency swell, the PVs should reduce their generation. The frequency swells happen when there is a loss of load in the system. But yes, rooftop PVs, the tiny ones, 3, 4, 5 kilowatts, they of course they cannot do much. But yes, if we can have an aggregated service, not physically, but if there is a controller sitting at the top of those PVs and they can instruct the PVs on the rooftop to provide such a service, virtual inertial service, that will be very helpful, especially for the low voltage utility grid. For example, if a grid goes into maintenance, the PVs are no good because it is not getting any frequency command. So the PVs also turn off unless there is a DG, a diesel generator, or any other frequency supporting source. So a PV as a virtual synchronous generator can perform black start capability if it is designed in such a way. And yes, of course, if the load and the insulation allows such a scenario, if the PV is to act alone, in case it is to work as a virtual synchronous generator. Now, to have a PV as a virtual synchronous generator, the general methodology of control is we have a cascaded controller, we have an inner current controller which takes care of the current protection, it takes care of the harmonics, and then there is an outer AC voltage controller which is responsible to control the AC voltage, and then there is another outer controller which is the power controller, which gives the frequency signals, because in case of PV as a VSG, it is no more a frequency follower. It will be able to generate its own frequency, although it's a synthetic inertia device. It does not offer real mass into the system. For this, we have the general Drew control law that is augmented to be with this term, which contains the inertial coefficient and the damping coefficient. We can have the PV being mimicked as a virtual synchronous generator. This is the general control methodology of the PV. We have the PV, we have filter, we have the outer inductance, which could be a transformer, it could be an LCL filter. So we have the PV references, and this is the PLL that is being formed. And then we have the voltage controller, which is like a virtual admittance. And then we have the DC voltage controller, which comes into play especially when the PV is working in the grid connected mode. So they keep switching between islanded and grid connected mode if there is, however, the grid behaves. And this is the synchronization controller. It's a very simple synchronization controller that we have developed, especially when the PV moves from the islanded mode to the grid connected mode. We have considered a real-time cyclate distribution system for our tests. We have community energy storage 80 kilowatt hour, which in reality generates 35 kilowatt peak. And we have 3 decks. So we have PVs distributed all around the figure, batteries, loads. But yes, I would give a small comment, a small disclaimer that in order to realize, the PVs as an aggregated service, the controllers were put together for all the PVs. These are some of the results we obtained using the real-time typhoon hill simulations. When we go from the grid connected mode to the islanded mode, the batteries and the PVs, they pick up power. They are part of different buses, so yeah, they still work in unison. This delay over here is only a recording delay. This is not the delay that is produced by the PVs per se. So yes, the PVs enter from the MPPT mode to the VSG mode as soon as the grid goes into islanding. And similarly, when the grid, we have the grid back, we can go from isolated mode to the grid connected mode, and we have seen that we can go back to the grid connected mode without having any kind of spurious transients, especially because of the synchronization strategy that we have developed. And these are some of the instantaneous voltage and current results that were obtained. So to conclude, yes, so when we have PVs operating in the grid connected mode, the system reliability is definitely improved, and the frequency and voltage deviations are also low, especially in the islanded mode, because they are supporting the frequency and the voltage of the system. And there were some issues while we were doing our simulations, real-time simulations using the Typhoon Hill. To eliminate those errors, we used core couplings to ease the CPU load of the Typhoon Hill. Thank you.
Thank you.